Welcome everyone to our 11th FAIRWork webinar. Today our colleagues from Jotne, especially Rishank, introduce us to how we use digital twins and knowledge bases in FAIRWork, so how we get the data and provide it then to the AI services. And without further ado, thank you very much for coming, everyone. And Rishank, the floor is yours.
Thank you, Christian, and good morning, everyone, and welcome to this webinar. And as Christian told, I am Rishank, and I am from Jotne. And this webinar is part of a dissemination activity in this project. And here I would like to talk about digital twins and how we are going to use these digital twins in the FAIRWork use cases. And the FAIRWork is an EU-funded Horizon project. And in this project, our primary focus is to leverage this digital twin data to provide decision support using AI services. And as a technological partner in this project, Jotne has 30 years of experience in providing standard-based software solutions, primarily focusing for product data exchange, product lifecycle management, long-time data archival and retrieval, and also data validation and verification. Jotne is also part of several research and development projects that are related to European Union and as well as European Space Agency, and several for other customers like Lockheed and Airbus uses our standard-based software solutions for data storage and data exchange. And our solutions are mainly implemented based upon Express Data Manager, which uses ISO 10303 step standard. And Jotne is expertise in providing standard-based software solutions. And then we will go to the agenda. During the next 20 minutes, I would like to talk about what is a digital twin and how we are going to use this digital twins and why we need this digital twin in FAIRWork manufacturing use case that is related to a car manufacturer called TRF, and then how we can create these digital twins using this standard-based repository that is ISO 10303 for this CRF use case. And furthermore, we will leverage the data that is stored in these digital twins for AI algorithm such that we can provide decision support for the use case scenario that I'm going to explore. We are going to explore in this webinar. And at the end, we will have some time for question and answers. Now, I would like to just establish a definition for digital twin system. As you can see, there are several hundreds of definitions to describe what is a digital twin, but here I am referring to a digital twin system that is a standard referred by ISO 30173. What is a digital twin here is a digital representation of a target entity with data connections that enable convergence between the physical and digital states at an appropriate rate of synchronization. What does this mean? The target entity can be a physical object, and in the real world, that can be a machine or a robot or a process or a human. And digital entity is an data element or a simulation element that represents the attributes of this physical entity. And data is the information that emulates the target entity into the digital entity. Furthermore, to have a successful digital twin system, we need to have a data communication between this physical entity into digital entity by an API method. These four blocks together make a digital twin system. And furthermore, we have other supporting components like infrastructure. The infrastructure can be an actuator or a sensor box or a high IoT hub that provides some information about physical state of a machine into the digital entity. Furthermore, we have these services. This is not really required, or it can be an additional add-on to this digital twin system. These services can be a simulation service that can use this data, or an visualization component, or like virtual reality, or an optimization algorithm which uses the data from this digital twin system to provide some decision outputs. Furthermore, the application domain is the area where we want to target or use these digital twins, like the manufacturing area or a healthcare sector or from in aerospace and defense. And the system aspects are related to the data aspects that we are going to store in this digital entity, like privacy and security concerns about the data and why and what data we are collecting, and furthermore the ethical aspects. So these are for additional add-ons that can be included in this digital twin representation, and this can be used for any service that want to use information and make decisions on physical entities in digital world. And having a digital twin, we can have real-time monitoring and control over the physical systems, as well as we can get a complete lifecycle management of these physical assets, as well as we can use the data for predictive maintenance as well. Now we have established the what is a digital twin. We will see the use case scenario that is in the FAIRWorks for CRF, and how we want to use these digital twins and use the data for providing decision support using these digital twins. So as I told you, this is a EU project, and in this project we have two end users. One is Flex, which is a robot manufacturing company, and the other company is CRF, who is a car manufacturer. And here we would like to focus in this webinar about the CRF use case, primarily workload balance. In this use case, actually, we have identified few scenarios where we can use AI to provide decision support to the decision support to enable a plant manager or a line manager who need to make decisions with the help daily based on the data. But here we would like to use AI algorithms to provide some decisions to the manager so that he can use this information as a supporting material. And here I would like to focus more on this workload balance scenario, and I would like to establish what is CRF plant and what is this scenario, and we will explore this scenario in the next slides. So what is a CRF plant? As I told you, this is a car manufacturer, and in this image you can see the 2D plant layout, and you can see the highlighted section of UTE1, UTE4, and UTE8. What are these sections? Or you can consider these are a part of a plant where they have different line configurations. On UT1 you have line 5, line 7, line 9, and line 11. So what are these lines used for? You have a raw material input, and these lines have a series of stamping machines which take this raw material, and they will make a stamp on these parts or mold them into a required part that is received at the end of this line. And at the end of this line, there will be operators who collect this finished material part and load them into a container. And these containers have specific container code and as well as number of pieces that can be fitted into this container. Apart from this, you have this other UT4 here. Also, these are other lines which use it to produce, again, they are used to produce the parts using this stamping process. But the difference between UT1 and UT4 is that parts that are produced on UT1 cannot be produced on UT4. Similarly, UT4 parts cannot be produced on UT8. So each line has capability to produce certain selection of parts, which we will see in the later slides. And then each section can only produce parts that are associated to these lines. Now we have seen this plant layout. We will also see what exactly we would like to achieve in this workload balance scenario. So in a given day, we have a production requirement that we need to produce, say, 10 parts in this line configuration, say in UT1 and UT4. So as you know that each part has a certain dedicated line, and in this line we need to have operators that need to collect these materials. So the scenario is described like this, that we need to, the plan manager takes the information of available operators in the given day, and also their training capabilities, like there is information related to operator training capability, that on which part he can work, or he is trained on this part to carry, like based on his age and their experience. The plant has information about this operator physical capabilities as well as medical conditions, such that whether he can work at the end of this line to carry these parts, because these parts can vary from size, shape, and length. So this information is available as a capability of operator, and the availability of operator information is required such that the line manager can see who are available on the given day, and then he can assign these operators onto the end of these lines. Furthermore, he need to ensure that on a given day the production plan requirements are met, and then also he need to look about the information about this container storage area and the raw material information, as well as the state of these machines which need to carry these containers. So on a given day, line manager, if there is a change in its production plan, he need to consider all this information, and it it takes some time for him to consider all this aspect and provide a right decision or a suitable decision that ensures which meets the production plan requirements as well as operator satisfaction level. So here in this case, what FAIRWork would like to do is to take operator preferences as well into this information and consider all these production requirements and capability of operators, and provide a fair and transparent decision that is accepted by all. And this decision is not the final decision. The end user, like the plant manager, will have control over this decision, and he can allocate the workers to these lines based on this algorithm output. Now we have established the use case and we have seen the plant layout. Now we would like to create digital twin representations of these systems into the knowledge base, which is a database component in this FAIRWork project, where we would like to use this database to create digital twin representations of entire lines, geometries, humans, operators, forklifts. We would like to replicate all this information as a digital twin entity into the system. So how can the knowledge base itself, as I told you, is an standard-based repository which utilizes ISO 10343 repository or a standard for operating this knowledge base, and we have capability to store digital twin or digital shadow representations, and we have this server application where user can access the application in an GUI on a web browser and utilize the functionalities provided by this repository to create required digital representations. And how we can do that is that if you have a step path of a plant layout like this here, if you have a, like, let's, as I've shown you that we have this 2D plant layout image, but if you have a 3D CAD model in a step format, you can leverage the capabilities of our standard based repository, and you can directly import this step file into our knowledge base or a repository, and automatic product breakdown structure will be created. On the right hand side, on the bottom of your screen, you can see this small blue color bordered box where automatic breakdown elements are created. And what are these breakdown elements we will explore in coming slides. But if you have a step model, you can directly configure these. And if you have a sensor information, let's say you have a machine that has a step model and you can import it, and you want to associate some sensor data like machine temperature, machine humidity, or some RPMs, and some other information like voltage or everything. That information can be configured using reference data library, which is a PLCS concept. And using these concepts, you can define the attributes like sensor properties, like the timestamp and the voltage rating. And based on this information, you can upload this data into the appropriate digital representation of this physical entity. So what is a reference data library? A reference data library is a collection of PLCS concepts which provide a comprehensive way to define required properties of a physical entity. Let's say you have, in this example, we have a geometry, as I told you, that each geometry is produced in a line, and this geometry have certain configuration information. Like to produce a geometry or a part, you need to have its raw material identification code, and then required series of these die numbers. Like as I told you that each line has series of stamping machines. These stamping machines need to have dies, and these dies have some identification code, and each geometry is associated with this die configuration information, and we can configure this information using this reference data library. And as well, that this geometry also has other properties like the container which it is placed. You can see this forklift here, and the containers which I'm talking about is in front of this forklift, and these containers have certain capacity that to hold maybe a 40 pieces of material of a certain geometry, or 100 pieces based on the type of geometry and the shape. You can see that you can accommodate more or less geometries based on the size and shape. So these kind of information are necessary to be there in this knowledge base, such that if you want to produce certain geometry in a line, we need to know that how many operators are required. Like you can see on right hand side bottom that OP is called operators required. That is 4 operators are required at the end of line to carry this geometry and place them in the container. So these kind of information about each geometry is required. And what we have done here in this scenario is on the right hand side top, you can see line 17. And in line 17, there are different folders. What we call them in the repository is the breakdown elements, and each breakdown element has a breakdown element type. And this type is what we are talking about difference data definitions, that we can create these properties like the material code, the required container code, and the number of pieces that it can carry. And furthermore, in these defined properties, we have other information like required stamping die numbers and backup line number, as well as required material identification code, such that we can established a comprehensive library of information that is required in this scenario. Now we have seen that how can we create, digital twin representations based on this physical entity. Either if you have a CAD model, you can directly import it into this repository, or you can use reference data library to create these required attributes or properties that defines the physical state of system, and we can associate corresponding values to these properties in our knowledge base. And this is the final output. Here on the left hand side, you can see a node graph which has been obtained. As earlier, I have introduced the use case scenario in 2D layout. Here we try to replicate same structure. On the top level, you have CRF. CRF is the plant, and we have corresponding units, UT1, UT4, and UT8. You can see these root child nodes expanding towards right hand side, and UT1 has its corresponding lines, and each line has their geometric information, where what geometries that can be produced. And similarly, we have UT4 and UT8. And apart from these, we also require furthermore data to store in the knowledge base in form of digital twin, such that we can leverage this data, and we will explore those data in upcoming slides. And here you can see the final output structure in more clear semantic manner on the right hand side picture, that we have UT1, UT4, UT8, and the tree structure showing the container information, data files, decision models, and etc. In the next slide here, now as I told you that in this workload balance scenario, we need to identify how many operators are present in a given day. So we need to have this information stored in this knowledge base, or this data repository. And here we have leveraged again this different data definitions to create this structure where we can take the information of available operators on a plant based on a given date, and this information can be stored in the system. And here is on the left hand side top, you can see that operator presence information in the list of data that is stored in the system. And the knowledge base itself provides an API endpoints for each of these breakdown elements, such that you can access this data, or you can also use the same endpoint or same node number to upload this data. And here on the right hand side, you can see the corresponding REST API JSON response, where we have extracted this information as a JSON format. You can also extract this information as a CSV as well. Furthermore, on the left-hand side bottom, we have also created this additional digital representation of each operator. Why we have created this is to take these operator preferences, such that we can use this data in decision-making process to allocate workers onto the lines. And in this element, what you can see is that we have these IDs of operators. Let's say 10,001, 10,002, it corresponds to each operator. This is anonymized data just created for this presentation, and each operator has his name, like the experience, and then the training capabilities, as well as we have created additional properties to provide his preferences to in a given day to work on certain line or a geometry based on his training capabilities. And this is what reflected here, that on a given day, certain day, the operator 10,001, he is saying that he has preference of 0.1 on line 17 and 0.8 on line 20 and 0.1 on line 18. So this kind of information can be updated using API endpoints and stored into the knowledge base. And furthermore, the next data which we are focusing here is the operator's training capability. Here, as I told you, that we need to also have this information that which operator can work on a geometry on a given line. So as you see here, the data what the end user have is in Excel format, and it is stored in these images like smileys and cross marks, which is not a suitable way to share this information to AI algorithms. So we need to modify and transform this data into a better suitable manner, such that we can leverage this data and use this data for decision making processes. And here, what does a smiley mean is that operator can work, and the cross mark means he cannot work. And having a digital twin representation of this data makes use to transform this data and have a standard format, as you see, which we have translated this here on the bottom right hand side, that operator ID and has experience to true or false, which is a simple representation of the data. And now we have seen that we have established the plant layout into the knowledge base as well as support requiring data. Here, the table on the left-hand side provides you a summary of information that how we have created this knowledge base and what are the endpoints and the type of data that has been created in this area in this knowledge base, so that the algorithms which need to use this data can access them easily by looking at this table. Let's say operator availability. So what is the data source? From the end user side, it is operator presence information, and then how it is stored in the knowledge base is with the name called operator availability. And what is the type of data we can expect from this is a Boolean value, and type of data is true or false. Similarly, we have this experience on the line, and then worker preferences and workers required. So having this table of data that summarizes that the user who want to use this information in their AI services can identify, look at this table and can make these services to accept this tabular data into their service, and they can directly use this Excel sheet or tabular data and make some algorithmic negotiations and provide decision support. And on the right hand side, you can see a microservice configuration framework, which is implemented by one of our project partner in this FAIRWork project, that is VOC, using Olive microservice framework. What they are doing here is, as I told you, that each data from the knowledge base has provided, say, REST API endpoint, and this endpoint can be configured into this microservice controller framework. And you can see such example here that we want to get the information of operator availability, and this is configured in this framework, and you can use this endpoint directly to any other application that you want to access this information. So based on this, we have done further use the Netflix microservice orchestrator. So what is this microservice orchestrator is now, let's say we require 5 data. So 5 types of data from the knowledge base in this workload balance scenario, like operator presence, the steward suitability, like the operator suitability, as well as the production line information, like which geometry need to be produced on a given line, as well as operator preferences, and which line and what is the geometry that need to be produced. So if an end user like AI software user who want to use this data may need to make 5 API calls or 10 API calls based on the configuration which we provide to access this data, make data transformation, and combine this data together to make a suitable structure that can be used for providing decision to provide, a output. But here, by this Netflix orchestrator, what we are doing is we are configuring each microservice earlier, in which is shown in earlier slide, that we are configuring each microservice and combining all the services into one endpoint, and this final endpoint will provide all the data that is required in a tabular structure. And based on this data, we have created an rule-based decision service, which is an AI algorithm which has implemented. What does this take is the on table 1 here on the picture 1, you can see on the left hand side that marked with 1, we have a production requirement on a given date that on line 17 we need to produce certain geometry, on line 18 we need to produce certain geometry, and we have production priority as well as due date and number of operators that are required. How we got this information is based on these digital twin representations about the material, and as well as line configurations. From material we got number of operators required, and from line configuration, we got this other information that is required, like production priority and due date. Based on this is our requirement today, and we want to allocate workers to these lines. And the second service, what it does is take the input from the one, and as well as the accumulated or combined data that is obtained from this microservice orchestration. And then this both information is fed into the algorithm, and then the algorithm has provided output on the right hand side. On image 3, you can see the decisions that are made based on the operator preference, their experience, resilience factors, and they have allocated the required workers. Let's say in 17 you have 6 workers based on the available data of pool of operators. Let's say in this scenario we have 115 operators. We have allocated 6 operators in production line 17 and 4 operators or 6 operators for 18 and 20. This is how we have leveraged this digital twin entity definitions in our knowledge base and the data into the AI services and provided decision support to the end user. Furthermore, what is the advantage of using this standard-based repository for creating digital twin system is that apart from storing the data and retrieving the data, we also provide better user role management. As I told you earlier, that in a digital twin system, that it is important that data is it is a aspect that is important, that who is accessing data and why they are accessing data is an important thing, and we need to have a control over the data access. And here in knowledge base, you have this subdomain management where you can grant access to certain user who can only access the data, read the data, or only view the data. Furthermore, you have one more flexibility here to compare the versions. Like here on the left-hand side bottom of your screen, you can see that comparison of versions of these digital entities, that is about operator records. Here you can see that on version 1, we have, let's say, 100 operators with operator IDs. And in version 8, what happened is that operator has left the organization, the ID with operator with ID 10,001. So we have deleted that operator. So you can see that what is the difference between version 1 and version 8 is that operator has left. So this state of information about each record can be also seen into this version and comparison. And it's not only about this deletion, we can also get this version information about change of a document or a system. So this provides a comprehensive overview of entire product lifecycle management. So let's say you have a machine and it has several components with sensors, and it has a breakdown or a failure. So you want to see after 10 days what has happened to earlier version of this machine, that you can see that there is an additional definition that has created that it has a breakdown and we have fixed it using a part, and this kind of information can be stored in this standard based repository. Apart from that, we can also provide the features like step file format import and export. So if there is a other system which handles this ISO 10303 standard based repository, then you can directly export this entire project structure into that, so you don't need to configure entire information again. So, and also there is also one other aspect that is important when we are storing like this data or the information, that we need to have this information that who has uploaded this data, when this data has been created, and when this has been last modified. So this kind of document management properties is also automatically created when this user is using this information. So user need not to bother about this information. So the advantage of having a standard-based repository for digital twin is you will get complete asset lifecycle overview, that who owns it, who made it, and what changes have been done in the entire system. So finally, I will conclude this webinar by few points that we have seen that what is a digital twin and why and how we have created these digital twin representations for the CRF use case in the knowledge base, and then how the data has been utilized in an AI service to make some decisions. And the important aspect is that we are also considering the operators preferences as well in the decision making process, which provides a fair, and at least we are trying to provide a fair decision that every worker is happy with the decision made by this algorithm. And also it has reduced the time and planning effort for an plant manager, that let's say in a given day, like if there is an operator is not present and he has already made a plan for a given day before 2 days, then he need to change this plan. So but he need to look at all the data that is required, but just using this service, the knowledge base, the digital entity will take care of all the data. So the decision service can directly provide all the required information to allocate workers, and he can say like, okay, whether he likes this output or not. And then finally, if you want to further know about Jotne standard-based digital twin representation, or you would like to get more information on how Jotne is using their software products to create these digital twins, you can feel free to attend this conference on 25th of June, which is going to be held in Oslo. And now the floor is open for questions.
Oh, first of all, I want to say thank you very much for this interesting presentation. And then, are there any questions from the participants? Okay, it doesn't seem this way, so you have explained everything well.
It seems so.
Yeah. So then, thank you very much for joining our webinar. And the last words are for you, Rishank. If you want to say something, then go ahead.
There is nothing much, but let's keep in touch. You can find my email ID on the top of the slide, and you can also find this webinar in YouTube soon. Hopefully, Kristen will do that and provide the required information. And
sure. If you want to know when it's online, you can follow us on LinkedIn. Then I will send out when it's published. Then thank you very much. Have a nice Friday, a nice weekend, and hopefully see you soon at the next webinar.